Hey guys, welcome back to Tech Canon, and this is chapter 7, algorithms. From here on out, we're going to start the algorithm series where I would be walking you through some common patterns for algorithm problems that are asked during software engineering interviews. A lot of these lead code style software engineering interview questions and how to approach them. For this first one, we're going to go over the two pointer algorithms. So we're going to be going over the valid palindrome problem. This is a problem that I picked from Leeds Code that I feel is a good one to use as an example to explain how two pointer algorithms work. So let's go through it one step at a time. Valid palindrome. A phrase is a palindrome if, after converting all uppercase letters into lowercase letters and removing all non-alphanumeric characters, it reads the same forward and backward. Alphanumeric characters include letters and numbers. Given a string, return true if it is a palindrome or false otherwise. So at least we know our return type for what we'll be writing will be a boolean. So we're going to return either true or false. And now for the evaluation of a palindrome, let's look at example 1 here. A man, a plan, a canal, Panama. So essentially what it says is after converting all uppercase letters into lowercase letters and removing all non-alphanumeric characters, it reads the same forward and back. So looking at example 1, if we convert everything to lowercase, which is what they did to arrive at the explanation portion, and they got rid of all non-alphanumeric characters. So it's already been defined that an alphanumeric character contains just letters and numbers. So any spaces in between letters, any commas, in this case, we see a colon after canal that was also taken out as well. And then we have just a string that contains every letter or number that was in that phrase. And if you check, how do we know this is a palindrome? If you read it for as AMANA, read it from the back, you have the same thing, AMANA. And then if you keep going that way, all the way to the middle, you see that they match. Example number 2 is essentially the same thing, all lowercase, got rid of all the white spaces, race a car. And if you see the word spells the same forward as well as it does backward. Example 3 is a case where we just have a space. Space is non-alphanumeric, so we don't consider that. And what we have left is an empty string, and an empty string reads the same backward and forward. So we could also call that a palindrome. So I guess with this, the first things we need to understand is what's the definition of a palindrome, and how do we evaluate a palindrome. So now let's go into the constraints. So the constraint section, we have 1 less than or equal to s dot length less than or equals to 2 times 10 to the power of 5. So this is essentially just defining what the maximum or minimum length of the string can be. The length of the string would always be greater than or equal to 1 or less than 2 times 10 to the power of 5. And then the other constraint we have is S only consists of printable ASCII characters, which means the string only contains characters. I don't want to explain ASCII characters now. You could take some time to look into that. The second constraint is that S only consists of printable ASCII characters. ASCII here means American Standard Code for Information Interchange. So essentially is a way to encode text. You could look into the definition of that more, but essentially for our purposes, we don't need to focus too much on that right now. Now let's look at the very first example that we had: a man, a plan, a canal, Panama. that evaluates output to be true. Before we can understand that example, it's always great to simplify your example. So create a smaller example to come up with an algorithm for you to solve the problem. So for this case, let's take the civic example. Given a word civic, we have capital C at the start, lowercase c at the end. But if you take a look at this, civic reads the same forward and backward. So civic is a palindrome, right? So how do we figure out if civic is a palindrome? Based on intuition, you could do one thing. You could read a string starting from start to finish, so meaning from position 0 all the way to the end of your string, and then you could read from position n, which is the end of your string, to the first, and then compare those two. But that is one way to go about this. If we were to do that in an algorithm, we'd have to read the same string once forward and read the same string once backward, and then come up with a way to compare those two, which can be a bit compute intense in that you're essentially running through your string twice, and then you need to find a way to compare. So how else could we do this more efficiently? One way you could think of is by checking, like I said, this is a 2-pointer problem. So you could set one pointer at the start of your string, another pointer at the end of your string, compare those two. We have C at the start and C at the end. So we're looking good as far as the definition of a palindrome so far, right? So let me walk you through the rest. Then we move our pointers each way from each side, since we saw that both C's matched. So now we shift them in. We have two I's. I is equal to I, so we're looking good in terms of a palindrome. We shift in to the middle. Now our pointers are in the middle at V. And essentially, because this is the middle, V is equal to V, so there's not much else to evaluate here. And since we're done and both pointers have merged in the middle, we can safely say that this phrase or word is a palindrome. Now, for example, if there was a point where in civic, one of the I's didn't match, we would essentially have just failed it and said, oh, this is not a palindrome, and returned false. So now let's look at the bigger example that we had in our algorithm problem. A man, a plan, a canal, Panama. How do we want to evaluate this? Like I said, we could read it forward and then read it backward and compare, but that would be the longer route. It would be much easier to have 2 pointers on each side which do the comparison until we get to the middle to determine if this is a palindrome or not. So in this case, we start at A on both sides. We have 2 A's, so we're good. We shift both pointers. Now we have 1 pointer at M, 1 pointer at a space. Now remember, in the problem definition, it says we're only evaluating alphanumeric characters, so only letters and numbers, no spaces, no commas, no special characters. So how do we move on from here? Since we're not considering spaces or special characters, we could go ahead and skip this space and then compare what we have next. So essentially the problem said if you removed white spaces or special characters. So since they said remove, we don't have to consider that. And then what do we do with our pointer in this case? We're essentially removing that space. And how do we do that? We remove that space by shifting our pointer to M to ignore that space in our evaluation. So now we shifted the left pointer one way to the right. So if you look at what we just did, when we started at A, we evaluated that 2 pointers matched. So left pointer, right pointer were the same. We shift them in. Now we saw left and right pointer don't match, right? When we were at M and space. But then space is not something we're considering. So we shift the left pointer by 1 to the right. So now we compare both again. Same pattern. M and M match. Whenever we match, we shift both the left and right pointer at the same time. So we move in. A matches here as well. So we shift both pointers inward. We have N on the left, N on the right. We shift both pointers inward. We have a comma on the left, A on the right. Remember, we're not evaluating spaces or special characters. A comma is considered a special character, so we could skip the comma. Now we have a space and A. Space is not being considered, so we shift the left again. Now we have A and A finally. So they both match. We shift both pointers inward. Now we have space and P. P is alphanumeric, so it's valid. Space is invalid, so we shift the left pointer in. So now, for example, I swapped the P in this one for a C on the left side because I wanted to show you what an example would look like if this was not a palindrome. So if C was here, this would not be a palindrome. And then at this point, we would have to evaluate C against P, right? Now, when we're evaluating C against P, they're both alphanumeric, so we cannot justify moving just one pointer. Since we can't move just one pointer and both of them do not match, would essentially return false at this point. So our phrase is not a palindrome if C was to be here, and we don't need to evaluate the rest. As long as we find a mismatch in alphanumeric characters, we return false. But our example had P here, not C, so let's continue with what we had originally. So we have two P's, they match, so we shift both pointers inward. We have L on the left, we have a space on the right. Space is non-alphanumeric, so we shift the right pointer inward. We have a colon on the right, it's non-alphanumeric as well, we shift it in again. Now we have L on each side, both of them match, so we shift both pointers. So I hope you can see the pattern now. Essentially shift both pointers every time we have letters that match. Then if a pointer is at a point where it is non-alphanumeric, then we have to skip that position and essentially move that pointer one step to perform the next comparison. So following the same pattern, this is what we're going to keep doing. A's match, N match. Now we have comma and A. The comma is non-alphanumeric, we shift left. The space is non-alphanumeric, we shift left. A's match, we shift both in. We have a space, so we shift the left pointer inward. And now we have both pointers merging as one. So as long as the both pointers can meet in the middle somewhere, this phrase is indeed a palindrome. So let's walk through our solution on LeetCode directly. 125, valid palindrome. So we have a function isPalindrome that takes in input parameter s, which is a string, and returns boolean, which is usually true or false. So now, if we were to walk through our algorithm that we just went over, so how would we express our algorithm as code in this function? So the very first thing we could do is initialize our pointers. We said we're going to have a pointer on the left and a pointer on the right. So if you take a look here, this is a simple definition of pointers. We have an integer left, which represents the left pointer, and a right pointer, which represents the right pointer that would be on the end of the string. So we set this to the start of the string by initializing left as 0. We're going to use 0 to refer to the very first element on our string, which is the first character of the string actually. And then on the right side, we're going to have the right pointer at the very end of our string. So to get the position at the end of our string, we can call the string.length method, which will return the string. Say we have civic, this would return 5. And essentially the right pointer would be at the end of the string, which is going to be the length of the string minus 1. We're going from 0 to n minus 1 in this case. So now we have our left pointer at integer 0 and our right pointer at the end of the string. So now we need to come up with a way to perform those evaluations from each side of the string till we get to the middle. Now, the very first thing we should do is define our loop. We're going to have to loop through the string till we get to the middle and figure out what we want. How do we know where we are at the middle of the string? You could just check if your left and right pointer have met in the middle, which is what we're going to do here on line 10, if you can see. So while left is less than right, meaning while we haven't gotten to the middle of our string, we are going to check the character on the left and check the character on the right. In our code here, how do we check for the character at the left of the string? So the character at method is a useful method that the Java string class provides for you to get what character is at a position in your string. And this position you provide is given an integer, which we used here by providing the position we are in on the string with our initialized int left integer. So essentially we get what character we have at position left, and we name it left character, and what character we have at right, and we name that the right character. So now we have our left and right characters. How do we do that evaluation that we talked about? So remember our logic was if the left and right characters are the same, then we shift into the middle. If they are not the same, we need to check if the character we're at is an alphanumeric character. So if it's not an alphanumeric character, that's the only time we shift one pointer without shifting the other. So if you look at on line 15 here, if you look at what we have on line 15 here, we're essentially checking if the character on the left, what we're doing here is checking if it is alphanumeric. So the is letter or digit tells you if the character is a letter or a number. So we have the exclamation point here, which is a logical not. So essentially line 15 is saying if it is not a letter or digit, then we shift the left pointer to the right. And how are we shifting the left pointer to the right? We just increment the left pointer by 1. So we shift it one way. Now, how we do exactly the same for the right character, else if. So what we're doing is if the left character is non-numeric, we shift it in. If that's not what the problem is, else if the right character is the one that is non-numeric, then we shift the right character inwards by reducing the count for the right character. Remember, right starts at the end of the array. So if we want to shift it inward, we have to subtract 1 from it. So we're going from, say, position 10 to position 9 on the array, going into the middle from the right. So now if those two conditions are not met, then what does that mean? It means we have to check if those letters match, since both of them are alphanumeric. So how do we check that? So we have the else condition. So once we've got into line 21, it's quite evident that both the left character and the right character are alphanumeric characters. So now we want to check if those two characters are the same, if they match. So on line 23, what we're going to do is compare the left character and the right character. So if left is equal to right, remember that's when we shift both pointers inward. But remember there's one key thing. Our algorithm shouldn't care if it's uppercase or lowercase. So it should be case insensitive. So how do we do that? The easiest way is to convert the uppercase to a lowercase, if any, and then compare those two characters. So Java has a useful method in the character class called character.toLowercase that can help us convert to lowercase. So we call this to lowercase on the left character and right character, So essentially, if either one of them is an uppercase character, it converts it to a lowercase. If it's already a lowercase character, then it just stays as a lowercase character. So on line 23, we have the comparison for both of them as lowercase characters. And if they do match, which we talked about earlier, we're going to shift both pointers inward. So to shift both pointers inward, what we do is shift the left pointer inward by adding one left plus plus and the right pointer by subtracting one right minus minus. So now we've evaluated the condition where the characters match. Now, else on line 26 is essentially the condition where we have, remember we evaluated both are alphanumeric already. Line 23, now we're checking if the two characters match. On line 26, it means the two characters do not match. It's the else condition of the match on line 23. So if the two conditions do not match, then we return false. That's the only point to return false, when we reach a point where the left and right pointer characters are not the same. So we return false. Now you're probably wondering, when do we return true? So we are going to return true at the end of our function. Essentially, let me zoom out on this a little bit so it helps. So we have our while loop, which we're using to evaluate the pointers all the way to the middle. So now we have the return true outside the while loop to essentially express that if this while loop completes, it means that yes, this is a palindrome, so we can return true. We return false inside the while loop at any point where we determine that this is not a palindrome. So now if we were to run this in LeetCode will evaluate this with different test cases, and as we see, it passes all three test cases. So that is it, valid palindrome using two-pointer algorithm. So let's talk about the time and space complexity of this algorithm. Time and space complexity is usually measured using big O notation, and going over this at the end of your interview is great because it shows your interviewer that you have an idea of how much time your algorithm is supposed to take given a particular input. So let's analyze the algorithm we just walked through, where we have to go through the characters from left to right till we get to the middle to determine if this is a palindrome or not. So let's start with the worst case runtime for this algorithm. The absolute worst case is that we have to check every single character in the string to determine if this is a palindrome in terms of time. So why are we saying that's the worst case? Because that's the maximum amount of time we'll need to spend to arrive at a solution given a string. So we move our pointers all the way from left and right sides to the middle. So given a string with n characters, we can safely say that the worst case runtime for this algorithm is big O of n, meaning it takes n in terms of time. Now, that's just analyzing the algorithm in general. Now, if we go into our code as well, we need to explain how our code is running in big O of n. So we initialize a left pointer here, a right pointer here. In terms of time, those are really insignificant since we're just initializing variables. Then we have a while loop. So whenever you are analyzing an algorithm's runtime, loops are one of those things you should look out for to help you understand the runtime of the code. So while left is less than right. So we're checking that while a certain position is less than the right position, we're going to still remain in this loop. So what are we evaluating in there? We're evaluating that as long as two pointers haven't met in the middle. And inside this while loop, all we're doing is we initialize a character here, initialize another, and essentially the rest of the code, the first line 16 to 18, just checking if the left character is a digit or a letter. 19 to 21 is checking if it's a digit or letter, perform an operation to decrement right. Then we have an else condition here where we now have more evaluations on the particular position we are on the string. So if you look at this high level, we have a big while loop that inside our while loop, all we're doing is evaluating if, else, and doing arithmetic operations. All of these do not take extra time, and so we would only be doing these operations on each of the characters, expressing that this is, again, big O of n, worst case runtime. Now let's talk about the space complexity. Well, if we wanted to go into details on how many bytes we're using, you could analyze the space that the left is using, the left pointer is using, the right pointer is using, and all of that. But for interview purposes, you only need to express the high level explanation of how much space you need. So we need a constant space to keep track of an integer, another constant one, and we don't initialize anything again until we get to line 13. We use one character for left character. We use another for right character. Now we're going to be reusing the left, right character because we're going to be changing these values. So left is being incremented. We're not defining a new variable. Right is being decremented here. And as we move our pointers, we're going to be analyzing each of the characters using left and right character, the exact same variable that we declared. So if you take a look at this, we didn't define any complex data structures like an array. We didn't define anything complex like a matrix or a nested array. The amount of space we're going to use for this algorithm is relatively going to be constant since we did not initialize any new data structures. We just have a constant list of variables that we're going to use all through the algorithm. So when we say constant space, it means the algorithm uses a fixed amount of memory that does not require extra memory depending on the size of the inputs. It's always going to be a fixed amount of memory no matter the size of the input. So the time complexity, to recap, is going to be big O of n, which is a linear algorithm, and then the space complexity is always going to be constant, and that is expressed as O of 1 space complexity. Thanks for listening to this chapter. Look forward to seeing you in the next one.